Okay. So we are going to do the little activity, the review activity on functional groups. Now remember that there's enough information in these little activity packets that you should be able to complete it without watching the video. So you're only watching the video to kind of check your answers once you've already attempted it. So make sure that you're attempting these on your own before you watch the video. So the first thing that we talk about when we talk about functional groups is just the hydrocarbon parent groups that they are in. So we know if something's a hydrocarbon, it contains carbon, and mostly it's carbon and hydrogen. You can have some other atoms, but typically it's carbon and hydrogen. And the carbon and hydrogen are going to form those covalent bonds, so they're going to share electrons. But remember that when carbon and hydrogen form a covalent bond and they share those electrons, they're going to share the electrons equally. So it's going to be a non-polar bond. And that's very, very important because that makes hydrocarbons very, very non-reactive. The more polar something is, the more reactive it kind of is. All right, so let's kind of look at them. So we have alkanes ending in ane. Those are going to be our saturated hydrocarbons. They're covered in hydrogens, so they have only carbon-carbon single bonds, and all the bonds are filled so that they have complete octets, and anything that is not a carbon-carbon bond is a carbon-hydrogen single bond. The next group, family group member, is the alkenes. These have carbon-carbon double bonds. Remember, 2 E's tell you that you have a carbon-carbon double bond. Then you have alkynes, and remember, alkynes are so kind and nice that they share 3 pairs of valence electrons, so that you have 3, a triple bond. So you have 3 of those covalent bonds. Then we have aromatic groups, and the aromatic groups are always going to have alternating double and single bonds. And when we talk about this, it's important to remember that there's a difference between aromatic compounds and cyclo compounds. Cyclo compounds are things that are a ring structure, but do not contain those alternating double and single bonds. So this is an example of a cycloalkane. It does not have those alternating double and single bonds, so it's not aromatic, but it is a cyclo compound. And so it's important to remember the difference between those two. So let's kind of look at these molecules. We got to answer a few questions first. Okay. So decide whether the following molecular formulas represent organic or inorganic compounds. Remember, pause it, answer it on your own first. So remember, for our organic, we need carbon and usually hydrogen and sometimes some other things. In A, I don't have any carbon, so that has to be inorganic. B, all I have is carbon and hydrogen. That's definitely organic. In C, I have carbon and hydrogen, and then we have this hydroxyl or alcohol group on the end. So it's carbons and hydrogens, and then you do have an oxygen, and that's okay. It's still organic. Then you have H2SO4. No carbon, it is inorganic. Okay. How are all the molecules in this molecule set the same? So when we look at this, every time that we see the end of a line or the junction of 2 lines, so everywhere where I'm drawing a dot here, everywhere here, these are all places where we have a carbon atom in the structure. And then each carbon atom, those bonds are shown if it's a bond between a carbon and a carbon. So for example, on this carbon right here, it has a carbon going to the next carbon, going up. That's this bond right here. Then it has a double bond here, that's the double bond, going down to another carbon. So I can look at this and I can say, well, that's not enough bonds to satisfy carbon's octet. So what it must also have are enough hydrogens bonded to it to complete its octet. So for example, the carbon that I selected, kind of erase this stuff, the carbon that I selected, this one right here, has one hydrogen attached to it. So what's common in all the molecules? They all have carbon and hydrogen, and that's it. I don't see any other atom, because if there was a different atom, I would have to show it. I would have to show it in terms of, let's say maybe I had a hydroxyl. I would have to show that OH, but I don't have any other atoms. So it's carbon and hydrogen only. All right, which molecules in the molecule set are polar and which are non-polar? So if we just said that everything in here is only carbons and hydrogens, let's kind of erase this, is only carbons and hydrogens, then by definition, they must all be non-polar. Because we said a carbon-hydrogen bond is non-polar, a carbon-carbon bond is non-polar. So if every single bond in all the molecules is non-polar, then all the molecules must be non-polar because they're just carbons and hydrogens. So based on the information, right, everything we did up here, these are hydrocarbons, just hydrogen and carbon. Are the hydrocarbons very reactive? Generally, no. So I would say no, with some exceptions. Well, there's always exceptions, right? If you have polar functional groups, that would change the reactivity of the molecule. And also if you have carbon-carbon double and carbon-carbon single bonds, and we'll talk about that later, that will change your reactivity. But in general, no, hydrocarbons are not very reactive. So the next one, we need to identify the molecules as belonging to different families. So what I'm going to do is I'm going to go up to the top. I'm going to kind of label each one, and then we'll come back down and put them into different categories. Okay. Our first one up here, this is a straight chain alkane, and I know it's an alkane because we have all carbon-carbon single bonds. It's a saturated molecule. When we go to 2, we see that we introduce this carbon-carbon double bond. When we introduce that carbon-carbon double bond, now we have to call it an alkene, E-N-E. And if we introduce a carbon-carbon triple bond, that would be an alkyne. Okay, then the next one, here's that ring with alternating double and single bonds. And so we call this a benzene ring. And if we're talking about functional groups, it would fall into the functional group of an aromatic molecule. So both of those would be correct. And technically, this is also a cyclo, C-Y-C, cyclo-al, and it's got a double bond, so alkene. So some things can fit in more than one category. Here we have a straight chain with a carbon-carbon triple bond, so that's an alkyne. Then we have 2 carbon-carbon double bonds. It's still an alkene. And then the last one is a cycloalkane. Okay, so if we would then go in and take that information and plug it into our family, for our alkanes, we would have 1 and 7. Then our alkenes should be 2, 4, and 6. Then aromatic would be 4. And remember, some of these are going to fit in different places. So if it's an aromatic, it's got carbon-carbon double bonds, so it's also going to be an alkene. So just remember that. So alkene, carbon-carbon single, alkene, then aromatic. Aromatic is that ring with alternating double and single bonds. And sometimes, remember, you're going to see it drawn like that. That's also correct. And then the last one is carbon-carbon triple bonds. And so we had 2 with carbon-carbon triple bonds. That's number 3 and number 5. And you could have actually created like another category of the cyclo, right? Things that are in a ring. And the things that are in a ring, we had 2 of them, which was 4 and 7. Okay. So you can always put them in more than one category like that. So what's the geometry of the carbon atoms in molecule IV? And what was molecule IV? That was our benzene ring. So here's a benzene ring, right? And you just have to have alternating double and single bonds. And it doesn't really matter where those bonds are, so long as they alternate. So if you pick a single individual carbon, each carbon has how many different areas of electron groups. So you can go to your best friend and you can go look and you can say, okay, it's got a single bond here. That's one group. It's got a double bond there. That's one group. Then don't forget that, just like we talked about earlier, it also has a hydrogen attached there. And so that hydrogen gives you a third electron group. So every carbon has 3 areas of electron groups. So now we know how many electron groups. Now we need to know how many outer atoms. So we have 1 outer atom here, we have 1 outer atom here, and then this is an outer atom. So 3 outer atoms. And what shape, molecular geometry does that give us? That gives us trigonal, T-R-I, trigonal planar. Okay, so every single one in a benzene ring is trigonal planar. Okay, so distinguish between an organic family of compounds and its functional group. So the families themselves are grouped by the presence of the functional group. So the family is grouped by the presence of the functional group. Okay, so everything is like that except for alkanes. Those are they're just carbon-carbon single bonds, so they don't have functional groups. So they're in their own category because they're all carbon-carbon single bonds. All right, so when a benzene ring's formed, right, we can have those double bonds that move. If this double bond moves to this place, then this becomes a single bond, this becomes a double bond. But you can't have a carbon, well, and maintain the number of hydrogens that you have without moving the next one. So each of these double bonds moves every time. And so you have these 2 structures that the molecule basically swings back and forth between. And so we draw it as this resonance hybrid. So remember that no matter how you see it in any one of these 3 forms, it's always representing the same thing. This one is just representing a combination of the first 2 structures. So it's not a big deal. Okay, identify the functional groups in the following molecules as belonging to the alkene, alkyne, or aromatic family. So if we have carbon-carbon double bonds, that is going to be alkene. And this is a carbon-carbon triple bond, so that's an alkyne, right? B, we have all those alternating double and single bonds. And so this would be an aromatic. The others are not aromatics because they don't have a double bond here and they don't have a double bond here. So it's just that first ring structure that's an aromatic. The next one, we have 1, 2, 3 double bonds, and so we call it an alkene. And then the last one, there's that 1 triple bond, and so we call that an alkyne. Okay. So next is, what is the formula for cyclohexane? And how does it differ from the straight chain alkane hexane. So anytime that you have something that is a cyclic or a cyclo, either way, it's saying the same thing. The last carbon is bonded to the first carbon. You can use the formula CnH2n. So if I counted my carbons, I would have 6 carbons in this molecule. And so that would give me a formula of C6. H is going to be 2 times 6, so that's 12. If I were to draw hexane, hexane is just a straight chain. It's still 6 carbons. So 1, 2, 3, 4, 5, 6 carbons. But it's going to have the formula CnH2n plus 2. So that would give me C6H. 2 times 6 is 12, plus 2 is 14. So there are 2 fewer. So on cyclohexane, cyclohexane, there are 2 fewer hydrogens, since the 2 ends, the 2 ends here and here, since these 2 bond to one another in a single bond, they lose a hydrogen. Since the 2, call them end carbons, bond to each other, they each lose 1 hydrogen. And that's how we go from hexane to cyclohexane, right? Okay, and then the next page, I gave you this. This is all the families. Now, we have to be able to recognize the different family/functional groups, right? So when we talk about different functional groups, it's important for you to hear a word and think about the structure. So if I have an alcohol, you should be able to, if I say alcohol, you should think it's some molecule that's bound to an oxygen that's bound to a hydrogen. And that is called a hydroxyl. So it's some molecule with a hydroxyl, and we call that an alcohol. And alcohols can be primary, secondary, or tertiary. So if we look up here at alcohols, here's our alcohols. See, here's our hydroxyl, hydroxyl, hydroxyl. So if we look at the carbon right here, I'm going to do it in green, that green carbon, this is the alcoholic carbon. So it's the carbon that's bonded directly to the hydroxyl group. And you look at it and you say, okay, how many R groups are attached to that alcoholic carbon? If you have 1 R group attached, it's primary. You have 2 attached, secondary. 3 attached, it's tertiary. So it's always talking about the number of R groups that are attached. The other functional group that you can have with an alcohol in it is called a phenol. A phenol is a molecule that has a benzene ring with an alcohol attached to it. So we call it an aromatic alcohol. So you have your aromatic group here, and you have your alcohol here. Yeah, so it's just a combination of the 2. All right. Then, okay, so we talked about alcohols, talked about phenols, we talked about the general form of alcohol. Amines. When you think about amines, I want you to think about nitrogen. There are 2 different nitrogen-containing groups. They are either amines or amides. So we'll start with an amine because amines a little bit easier. So if we come up here and we say, okay, here's our amines. So whenever you see nitrogen, you're going to be trying to pick between amine and amide. And the difference between an amine and amide is that amines are not bound to a carbonyl. Amides always have a nitrogen bound to a carbonyl. Okay, each one of these is a carbonyl. So you see a nitrogen, and that nitrogen's bound to a carbonyl. Nitrogen bound to a carbonyl, nitrogen bound to a carbonyl. Those are amides. Amines are nitrogens that are not bound to a carbonyl. But like alcohols, they can have that primary, secondary, tertiary, and quaternary designations. So nitrogen usually, right, likes to make 3 different bonds and leave a lone pair. But what can happen is if you take those lone pairs and that nitrogen donates both lone pairs to another something else, it becomes protonated because it donated both electrons, so it becomes positively charged. And that's why they call it protonated, because it's positive. Okay, so a primary amine is a nitrogen, so here's my nitrogen, that's bound to only one R group. A secondary amine is a nitrogen that's bound to 2 R groups. A tertiary amine is bound to 1, 2, 3 R groups, and a quaternary amine must be protonated, and it is attached to 1, 2, 3, 4 R groups. So either the nitrogen is bound to R groups or to hydrogens. To determine if something is primary, secondary, or tertiary, you look at the number of R groups. All right, so let's see. Okay, and then if you look at the general form for a primary amine, if it's a primary amine, there's only 1 R. If it's a secondary, there are 2, tertiary is 3, quaternary is 4, and the nitrogen is protonated. All right, carbonyl containing compounds. Carbonyl, we said, if you have a carbon double bonded to an oxygen, right, there's got to be 2 other things attached to it. But this carbon in the double bond to the oxygen, this is the carbonyl. And so when we talk about things that have carbonyls, if you come up, all of the functional groups kind of on this side have carbonyl functional groups in them. So, for example, if you had a carbonyl that is bound on one side by a hydroxyl, so here's your carbonyl bound to a hydroxyl, we call this carboxylic acid because the hydrogen right here can leave the molecule, and if the hydrogen leaves, now the oxygen's carrying a negative charge. So we call this a carboxylic acid because you can lose a hydrogen. And then if we lose that hydrogen, now we call it a carboxylate because it's an ion now. So carboxylate ion. Let's see. I'll keep just chatting. I got to come back to this. Okay. So we said the carboxylate form of carboxylic acid is ionic. We said that. Okay. So then, sulfur containing compounds. So these, anytime you see something that says thio refers to sulfur. So if you come up here, if you have something that's a thiol, that means you have a sulfur and it's bonded on one side to the rest of the molecule and it's bonded on the other side to a hydrogen. If you have a sulfide or a thioether, remember an ether up here is ROR. So a sulfide or a thioester, a thioester, thio meaning sulfur, and ester meaning R something R. All you do is take that S, and instead of having an oxygen where the X is present, you put the sulfur. So you have an RSR instead of an ROR. They look very similar. Only difference is either a sulfur or an oxygen. So you just gotta work on memorizing these. All right, let's see. A phosphate group. Phosphate group is really cool. Here we go. Because a phosphate group carries a charge. So you have a phosphorus atom in the middle, and that phosphorus atom actually makes 5 bonds. And one of those bonds goes to the rest of the molecule. One of those bonds goes to a negatively charged oxygen, the other one goes to a negatively charged oxygen, and then the last two are involved in a double bond to an oxygen. And so a lot of times you see phosphate groups as molecular switches. So if a phosphate group is bound to a protein, it'll either turn the protein on or it'll turn the protein off. Okay, and I think that's kind of the big ones. Aldehyde is similar. It's got a carbonyl, just like a ketone. But remember, an aldehyde is all alone, and so it only has one R group, whereas a ketone has two R groups. And I like to think about it like a lock and key. So you have two R's, like you have a lock and a key, 1, 2 things. What else didn't we talk about? We didn't talk about an ester. An ester is very similar to an ether, because remember, an ether was ROR. So all we did was to go from an ether to an ester, we said R, I'm going to bond it to something, and then OR. That something is a carbon in a carbonyl. So ester and ether, very, very similar to one another. An acetyl is that R bonded to the carbonyl, and then that carbonyl has a methyl group attached to it, just one carbon containing group attached to it. Okay, I think we've hit on them all. Okay, so let's come down and kind of look at some different molecules, because lots of molecules have more than one functional group. Like they're pretty complex. And so if you can identify functional groups, you can really actually predict how the molecule is going to behave. So one of the ones I like to be able to identify right away, very easy, this big bulky one, this is a benzene ring. And so we know that this falls into the functional group category of aromatic. It's like when I see it, I immediately want to write it down. And then one of the things that you can do is you can kind of look for things that have carbonyls. So I know that this is a carbonyl. This is a carbonyl, but that's not really a functional group. And so to identify functional groups, you have to look on the sides of the carbonyl and say, what's going on? Okay, well, I have here a carbonyl, and on one side it's bound to a hydroxyl, and on the other side it's bound to basically the rest of the molecule. So I have R bonded to a carbon and a carbonyl bonded to OH. So that would be a carboxylic acid. Okay, so that's our carboxylic acid right there. Then kind of towards the top, I have a carbon and a carbonyl. It's bound to an oxygen, and that oxygen's bound to a carbon, but usually we just put an R. And then this side, as we go this way, we're bound to another carbon, but we're just going to call that an R group. So where do we have R, carbonyl, OR? This would be an ester. Okay. So if you went in and you said, and let me circle that, that's an ester. If you went in and said, okay, well, I have a hydroxyl here, I have a carbonyl here, that would be true, but incomplete. So make sure you look at the kind of all the possibilities. Okay, for this one, let's kind of go from left to right. Now this is really cool because this is called an amino acid, and you're actually going to find out why it's called an amino acid. So here on the end, I have this nitrogen that's carrying a positive charge. It's bound to 3 hydrogens and an R group. So that is nitrogen, there's my R group, and then I would give it 1, 2, 3 hydrogens, and that nitrogen's carrying a positive charge. So this would be a protonated, if it carries a positive, it's protonated, primary amine. And so what do they call this? An amino. Oh, that's where the amine comes from, amino. Then if I look along here, carbon, hydrogen, oh, I hit a carbonyl. So I'm going to look at that carbonyl. Here's my carbonyl. What do I have going this way? I have an R group. What do I have going this way? I have an O minus. And so this is a carboxylate. All right. But depending on the pH, sometimes what happens is you have that hydrogen that came off. Remember to go from the carboxylic acid to the carboxylate? Well, that hydrogen can come back under certain pH conditions. And so we would have an amine and a carboxylic acid, a CID, and a carboxylic acid. So that's where we get the name amino acid, because it's a carboxylic acid hooked to an amine. All right. Next one is acetaminophen. This is primary ingredient in Tylenol, right? So automatically I see, oh, that's a benzene ring. But when you look at that, you go, wait a minute, there's something else attached to it. There's a hydroxyl. So you could say, okay, this is an aromatic, and this is a hydroxyl. But you would also have to say that this whole thing, an aromatic bound to hydroxyl, is a, you guessed it, phenol. All right, now we're going to move up. Oh, I see a nitrogen. So now I'm thinking either amine or amide. If I have a nitrogen that's attached to a carbonyl, and I do, then that must be an amide. Okay, not too bad. You just got to keep kind of practicing with these. Okay, consider the variety of local anesthetics shown below. How are they the same? How are they different? So it's important to kind of be able to look at molecules and go, oh, they kind of have the same function. So what structurally do they have in common? And so if you look at these, let's kind of see what we have a lot of. I'm seeing this benzene ring, right? I'm seeing this in, that's 2, 3, 4 of the molecules, 5 of the molecules, 6 of the molecules. Oh, they all have this benzene ring. The benzene ring is relatively nonpolar, right? Okay, and then we got some more nonpolar things over here, like these carbons are nonpolar. All of that's nonpolar. Nonpolar. Okay, then here's this ring. This is carbons. It's just kind of drawn in 3 dimensions. Kind of hate it when they do that, but this is nonpolar. This is nonpolar. So we have a couple of nonpolar portions to our molecules, right? Okay. And then what else do you see in all of them? Let's try a different color, green. Oh, look at this. We have a carbonyl containing group here. We even have it here. We even have it here. We have it in every single molecule. We have some kind of a carbonyl containing group. Now, as we kind of look at them, they're a little bit different, right? If I have a carbonyl next to an oxygen and it's got an R on either side, that's an ester. But over here, I have a carbonyl with a nitrogen, that's an amide, right? So they're not all exactly the same. Here's another amide. Let's see, what do we got down here? This is an ether, an ester, not an ether, an ester. Here we have another ester. Okay, let's see, what do we have over here? Another ester. Okay, another ester. Okay, so we have some kind of a carbonyl containing group in the middle of all of our molecules. And then what else do we have that's common across everybody? Blue. Oh, I have some kind of, oops, that is not a highlighter. We have some kind of nitrogen containing group, right? So all of these are amines. I don't see a nitrogen bound to a carbonyl, so there are no amides, but they are amines, right? So we have esters, we have amines, we have some nonpolar aromatic benzene rings. So every one of these molecules has a nonpolar portion. They have a carbonyl group kind of in the middle of the molecule, in the central part of the molecule. It's either an amide or an ester, and they all have an amino group. So if they have similar structures, they probably have similar functions, and we know they're all local anesthetics. Okay, let's do some more identifying. Circle all the functional groups except for alkane, because that would be a lot of circling, and provide their family name. So what you should have done already is, I'm going to go left to right on the molecules, and here I have a nitrogen right here, and we know if that nitrogen is carrying a positive charge, it's got 4 different things attached to it, and all those 4 things are R groups, so we're going to call this a quaternary amine. Then as I go along the molecule, I find an OH, that would be an alcohol, and if I look at my alcoholic carbon, how many R groups are attached to my alcoholic carbon? That's 2, so it's a secondary amine. Then on the end, I get to a carbonyl, and what's attached to that carbonyl but an O-, so this would be a carboxylate ion. Okay. Next molecule. Here we have an aromatic. Those are nice and easy to see. Then as we go up here, we have a carbonyl that's bound to an oxygen that's bound to an R group. That's an ester. And I come down, ooh, another nitrogen, and that nitrogen is bound to 2 different R groups, so we call this a secondary amine. Next one, this is our methionine. So what we have here is a sulfur in here. And so when we look at our sulfurs, remember there are 2 different kinds of sulfurs. There are thiols, and then there are thiol ethers. So this is an RSR, and so that makes this one a sulfide or a thioether. Either way would have been correct. Then as I keep going and looking around, let's see over here, I have a protonated amine, and it's a primary because it's only bonded to 1 carbon. So it's carrying a positive, so it's protonated. It's a primary amine. Okay. Then on the other side of the molecule, it's a carbonyl bonded to an oxygen carrying a negative charge, so that's a carboxylate. Let's see, lidocaine. So this is another one of those anesthetics. So this is an aromatic. Then we have here a nitrogen bonded to a carbonyl. This is an amide. Then, we have a nitrogen that's bonded to 1, 2, 3 R groups, and so we call this a tertiary amine. Just be careful on that. Okay, here we have an aromatic. That aromatic is attached to 2 different alcohols, and so we would still call this whole big thing a phenol. Then as we come over here, okay, here's a hydroxyl. So I look at this carbon that's attached, the alcoholic carbon, and I go down, that's 1, 2 R groups. So that's a secondary alcohol. Then what else do we have? Oh, a nitrogen bonded to 1, 2 R groups. So this would be a secondary amine. All right, let's go on to our next molecule. I see another aromatic. But in addition to that aromatic, I see that benzene ring attached to an alcohol. So I'd call that a phenol. And then I don't see anything else. So that covers our entire molecule. So you just need practice. The more you do, the better you're going to get. All right, hope that helped.